I'm going to go through these slides just real quickly, flashing through them to give you the opportunity to ask questions, because this was the video that was posted for Friday, and then we'll get into the combination bands and overtones and finish that up, hopefully in time to just do some review questions for the test, okay? So the main point of all of this lecture was really to emphasize the rovibrational transitions and get you to think about the difference between lines and levels. And so with each of the spectroscopic transitions, what I'd like for you to be able to do in this course, not just this section, but the whole course, is to say for a given spectroscopic phenomenon, whether it's visible transition, rovibrational, you should have in your mind what kind of energy levels are involved. And to recognize that if you're taking a spectroscopic measurement, that's the difference between two levels. And those levels are quantized, that's the need for quantum chemistry. And so you should be able to think about what are the quantum states that are being connected with light. So we have a spectral line that shows up in a particular place in a spectrum, and that's connected to two different energy levels. If it's absorption, it's going from a lower level to a higher level. If it's emission, it's dropping down. If it's scattering, it may be some other strange, like two photon process, but it's still connecting two energy levels. And so you'll see this emphasis throughout this whole set of notes, that there's levels and lines. The spectral lines are what we actually measure in experiment. So were there any questions about the Q, P, Q, and R branches? Which one's the lowest in energy of those three? The P. They go in alphabetical order, so the lowest frequency transitions will be the P, then the Q in the middle, and then the R on the high side. So we looked at the ramifications of symmetry on this slide. We looked at comparing CO2 and water, how CO2 is a linear molecule, it's symmetric. Now I said that a symmetric molecule is anything that has a threefold symmetry or higher. Well, what about CO2? What makes it symmetric? What's the n-fold for CO2? Like how symmetric is CO2? Infinity. Yeah, so it's greater than 3. Right, a C infinity axis is one dividing the rotation, one full rotation divided by infinity, and the molecule is returned. So we compared these two molecules, showing also that water was an asymmetric top and essentially has 3 different rovibrational sets of peaks. Then in the video we calculated this using the selection rules of delta V plus or minus 1 and delta J plus or minus 1 and 0. We came up with the different frequencies for the P, Q, and R branches. So these are going to be used in your lab, your rovibrational lab, where you have, for the P branch, you see that vibrational frequency subtracts 2B for every J value. And so if it's the J, it's the 5th J line, then it's 2B times 5, and that's subtracted from the vibrational frequency. So as I go higher in J values, it's subtracted even more. So J equals 50 to 49, because it's a P size, so 50 to 49 is going to be J equals 50 times 2B, and you subtract that number from the vibrational frequency. Now you could do that all by hand, or we could use Excel, and we could assign those J values, and we could run a linear regression to get the slope as it depends upon J. That slope is 2B for the vibrational, direct vibrational experiment. Raman is going to be 4B. I put this in here and basically told you this is note card bait. So if you're given a row vibrational spectrum, and I think there's one in the practice test too, you're given a couple of rotational lines and asked what's the bond length. You take those rotational lines and you get B, and you want to convert B to bond length. This is B up here. Look how complicated it is. It has Planck's constant, speed of light, reduced mass, pi, and then all of the unit conversions associated with getting into or out of wave numbers. And so this is that calculation. And that's a real pain to enter into your calculator. But if you're constantly using B to get to bond length or even reduced mass, those are the only 3 variables that you want. You want B, you want reduced mass, and you want bond length. Everything else is a constant. Pi is not going to change. Planck's constant is not going to change. And so you want to collect all of those things into a simple constant If you multiply all of those things that don't change together, you end up with this 16.85. And that's really nice because this allows me to use bond lengths in angstroms. It allows me to use the reduced mass. Instead of getting everything into kilograms, I can use grams per mole. And I can get my rotational constant and wave numbers. Or if I find a rotational constant value from a spectrum, I have two rotational lines, I take the difference between those two, that's 2 times B, so I divide that number by 2. Now I have B. If I know what kind of molecule I'm dealing with, like carbon monoxide, I have the reduced mass. And so I can use B and the reduced mass to get the bond length. And so here's an example. So I have F2 and calculating the reduced mass at 38 grams per mole for each fluorine. The reduced mass is 9.5. And I see that the S branch lines in the Raman spectrum are 3.56 wave numbers apart. And so I can use that information to get the bond length in this molecule. So walk me through the steps. What is the first thing I do? I've got 2 S branches. They're 3.56 wave numbers apart. And this is a Raman experiment. And I want to get to the bond length. So the Raman spectral lines are how far apart? 4B, because it's Raman. Okay, so I take that 3.56 and divide by 4. And now I have B. And so then that's where this is shown down here at the bottom. This 3.56 divided by 4, that gives me B. I have the reduced mass. I have that constant that converts all of the units. And my bond length is 1.41 angstroms. A whole lot easier than typing in Planck's constant, speed of light, converting from angstroms to meters, converting from grams per mole to kilograms using Avogadro's number. So all of those things that you will screw up on, typing instead of 10 to the minus 34, you type in 10 to the 34, and then your answer is 68 degrees, factors of 10 off. And you're like, what happened? So there's lots of places this can go wrong. These are the Raman O, Q, and S branches. And so if you look at that energy level diagram, you can see now they're jumping by 2. It's going from like 3 to 5, or from 1 to 4, and so on, or 1 to 3. And so then,
I'm sorry, I didn't see.
Okay, so go back here. We have the lines and levels. If you look at this S branch line, it starts at level 3 and it ends in level 5. And so delta J is equal to plus 2. It's going from 3 to 5. And we know that now because that's an S branch line. So these things are the same. If I see an S branch line, that means delta J is plus 2. If I'm in an O branch line, I'm starting here at level 5 and going up here to level 3. And so that's delta J equals minus 2. And that's the same thing, what we mean by O. So we've used these labels like P, Q, R, O, Q, S as shorthand so that we're not always writing J's everywhere, right? So we have an S3 line right here. This line is an S and we subscript 3. And so that tells us what J it starts at, and then the S tells us how it jumps. So this, just using this terminology, we can say this goes from J equals 3 to 5. And then this one, I picked this one here, that started in 5 and went down to 3, so this is an O5 line. And so that means J goes from 5 to 3. So you've noticed the subscript is always the lower J value. And then the S or the O or the Q tells you how it's changing. So what would a Q5 be? The 5 is the lower one, so we know it starts at 5. What does the Q branch tell us?
Jump is 0.
The jump is 0, so it goes from 5 to 5. Now you say, well, there's no transition. Yes, there's still a vibrational transition. So the vibrational motion is changing, but the rotational quantum number is not changing. Now this is pretty esoteric stuff. These are the rovibrational lines. You think, well, when am I ever going to run across this? The telecommunications industry uses this very thing because they're trying to send signals to and from satellites through the atmosphere. And what do you think is in the atmosphere? CO2, methane, lots of little molecules that rotate and vibrate. And they need to know where all of these lines are. So they will shoot signals between these lines. They will lock their frequency generator, the signal generator, in between some of these rotational lines and use that little window, and they will send their signal in between them. So they need to know exactly where these frequencies are. They need to know the landscape, the spectroscopic landscape of the atmosphere, and this terminology is used, and they'll say we're locking our frequency on the R15 line of CO2 or something like that, and then you know exactly where their signal is being sent. So for the Raman spectroscopy, we can put in the selection rules and come up with the frequencies. So now these are the transition equations for the OQ and S branch. And so you can see this difference here. You've got the Raman shift for the vibrational transition, and then you've got a constant, like an offset, 6B here for the S branch, or 2B for the Q branch, and then you have this slope here. So the quantum number J increments linearly, and you have this slope of 4B in the Raman. If it's the O branch, it's shifted from the incident frequency, and so it goes over to the vibrational frequency and then comes back a little bit. And so this is the it looks like it's adding 4B, but it's a shift, so it's subtracting a negative number, which makes it positive. But the point is, you've got a slope of 4B, so the spacing in Raman in each of the O and S branches is 4B, and that allows you to get that rotational constant. And so you've seen the joke, perhaps, if you saw the video. Okay, so it's 2B or not 2B. We know that it's 2B if it's vibration and absorption, and it's 4B if it's Raman. Let's look at this on your phones and see if we can put this into action. Excellent. Waiting on anyone? Okay, making sure. I thought I counted 31. So the rotational branches in an IR vibrational transition are called very good. It's just PQ and R. So when we say IR, we're just Raman is typically using visible lasers, and so it would not be, when we say IR, we're implying that it's direct absorption or emission. Okay, what about the rotational branches in a Raman vibrational transition? Very good, OQ and S. Now, why would it not be all 5? Well, because there are 2 different types of experiments. And so you have an infrared spectrometer that's doing direct absorption or emission. It's got a different detector, different source. than a Raman setup. So we really don't ever have them together. Yeah. So that's why you would really never see in the same experiment all 5 put together. Okay, what J values are associated with an O10 line? So now you're going to understand the terminology. What is an O10 line? It's telling you 3 things. It's telling you the lower J value, how J changes, and what experiment it is. So what kind of delta J there is. All right, good job. So the O10, that 10 tells us that it's J10 to something else. So it's starting in level 10. So we have 2 options there. Now I can go to 12 or 8. It's changing by 2 because it's an O line. O is Raman. So we know J is changing by 2, but is it going up or down? Since O is less than Q, it is less than S, that's the lowest one, so it should be going down by 2. So it's 10 to 8. That's how we got to 10 to 8. Let's try again. What J values are associated with an R10 line? Very good. So the 10 tells us it's starting in a 10, or the lower J value is 10, and it's going up to 11 because it's an R line. Okay, so then let's back up a little bit. What is required for molecules to display rotational lines in their vibrational spectrum? So you've got an FTIR spectrometer. You see rotational lines on top of their vibrational spectrum. You can know something about the situation. All right. Well, gas phase is the only time you're going to get rotational lines. Okay, and so notice our benzene, chlorobenzene spectrum didn't give us any rotational lines. If we had benzene vapor, we might have seen some P and R branches, but we had liquid benzene. You could put solids on the ATR and so on, and you would get a vibrational transition, but you wouldn't see any rotational lines. Why is it not permanent dipole moment? That's pure rotation, which would occur in the microwave region of the spectrum, okay? And it doesn't have any vibration at all, so it's just rotating. So a molecule that's just doing rotation excitation is the one that has to have a permanent dipole. And that's down in the microwave region. Very rare that we would have those experiments because the microwave spectrometers are not really that useful. They're not very, I don't know that they're commercially available. But FTIR is, everywhere. And so you won't see rotational lines in your FTIR spectrum unless you have a gas phase sample. And you do see them in almost every FTIR because you have water and CO2 in the atmosphere. So even though you're taking a liquid or solid sample, you see some rotational lines, that's probably not your liquid or solid sample. It's something in the air around your sample, either in the spectrometer or in the little sample chamber. And most of the time it's water and CO2. But like one time I told you I sprayed methanol in there and I got nice rotational spectrum. Now, you can get rotational lines from an asymmetric top, so it's not related to symmetry. Water is an asymmetric top and it has a rotational vibrational spectrum. It's just messy. You won't be able to understand how to determine what the rotational constants are, but you would definitely see rotational lines in the vibrational spectrum of water. And then linear structure, no. Nobody was fooled by that one. Very good. All right. So let's go on to the combination bands. This one's pretty short. I just want to show you that the symmetry rules can be expanded. This is probably the largest use of the direct product table that we'll see in the whole course.